entangled, and he will try to identify similar features in quantum dots.
All right, so as Dimitri said, I'll be doing my final presentation on Polaron states for infrared emission in perovskite quantum dot. So first, just like a real quick overview of quantum dots. They're nanoparticles of semiconductors, and they have these special properties due to their small size, and with this allows the transfer of electrons, which makes all this possible with the light emission when they're excited. And then a couple applications. A huge application for this right now is TVs. Samsung makes a QLED TV that uses this technology, which allows them to get these very nice colors with deep contrast. Another application with the perovskite quantum dots in particular is solar panels, which is becoming a more used technology due to their high conductivity. So some of the important equations in this project here, obviously the Hamiltonian, and there's a couple different stages of that, as well as the evolution operator, which allows us to kind of see where these things are going to be going, and then a few other parameters here, and the Arrhenius equation, same as Eungyo's, looking at activation energy. So there's a few different videos here. The first one is at a lower P0, which is the initial momentum of this curve. It goes from the blue curve, which is the excited state, down to the ground state, which is the red curve. And it is seen that the vibration is a lot higher in the ground state as compared to the excited state. It kind of goes slow, but
it's okay. Slow is good.
And then this is another one at a much higher initial momentum. And so this one ends up moving a lot quicker. And as you see in this one, the ground state is taking a lot longer to fluctuate. It's got a lot less vibrational energy because of this higher initial momentum. And then, so for some data collection, the way that it was done is to determine the rate, rather than being able to use the rate that came out of the code. It is seen here that it's averaging this this overall rate, whereas it has to just be done y over x and calculating the rate that way because of the drop off at the other end. That data is not good for the collection. It throws out the average. And with this, the Arrhenius Plot was made using the 1/temperature along with the rates that were gathered. And within this collection of data points, there was, on the two extremes, a lot of discrepancy in the data, whereas in the middle, it leveled off and formed a nicer curve in which this plot was taken from. And here, from here, the slope is where we get our activation energy from. Any questions?
Well, let's thank Morgan for the presentation. And paper is open for discussion and questions.
On your slide that had